Let's look at a couple of galvanic cells with non-standard concentration conditions, but we'll keep the temperature at 298 Kelvin. Starting with a zinc aluminum cell, you can look up the standard reduction potentials for aluminum zinc, and you can see that aluminum tends to be oxidized under standard conditions relative to zinc, so the zinc cations would be reduced. And that sets up this cell as the aluminum anode and the zinc cathode. The anode the site of oxidation and the cathode the site of reduction. So you could draw in the direction of the electron flow or the current from anode to cathode. The electrons are coming from the aluminum atoms, which then turn into aluminum cations in solution. And the zinc cations in solution are going to be reduced at the cathode and turn into zinc atoms. We want to assess the cell potential difference between these two half cells when the solution concentrations are not 1 molar. So let's look at the balanced equation or reaction from the two half reactions. You see, in order to balance the 3 moles of electrons lost from aluminum and the 2 moles of electrons gained by the zinc cations, that there has to be a multiplier of 2 and 3 respectively, giving us N equals 6 moles of electrons per mole of reaction. The standard cell potential difference, which we're going to use to get the just general cell potential difference, by flipping the sign for the oxidation reaction, we get 1.66 joules per coulomb. For the oxidation of aluminum, you add up the cell potential differences from the two half cell reactions, and you get an E standard cell of 0.90 volts. If you look at the reaction quotient at any given time for this reaction, it's product concentrations divided by the reactant concentrations to their coefficients as exponents from the balanced equation. The solids, though they have certain density or concentration, those concentrations cannot change, so they are never included in Q, that is reaction quotients or equilibrium constants. So the concentration of aluminum cation aqueous squared divided by the concentration of zinc cation aqueous cubed will be Q. And then we use the Nernst equation, the empirically discovered equation. E cell equals E cell standard minus, at 298 Kelvin, RT over F, the Faraday is a constant, of 0.0257. We divide by N, 6 moles of electrons per mole of reaction, times the natural log of Q, which we have delineated over here. So we can see that by just going back to kinetics, having a relatively larger concentration of the zinc cation compared to the concentration of the aluminum cation, Q would be relatively small. The natural log of a small fraction less than 1 is going to be a negative number, and we'd be subtracting a negative from E standard, and then E cell would be more positive than the E standard cell. So basically, by increasing the rate of the forward reaction more than the reverse reaction, we could generate a higher than standard cell potential difference. On the other hand, if we started with an initial condition of relatively high aluminum cation concentration compared to zinc, Q would be large. The natural log of Q would be some positive number, the natural log of a fraction greater than 1, and to be subtracting a number from a positive number from E cell standard. So that would give you an E cell that's less than the standard cell potential difference. So graphically, what we're doing is shown over here. If we had 1 molar aluminum cation concentration and 1 molar zinc cation concentration, Q would be 1 molar squared over 1 molar cubed and that would just be 1, and the natural log of 1 is 0. So the right side of this equation after E standard would just be 0, and the cell potential difference would just be the standard cell potential difference, which is where that line crosses the y-axis at x equals 0 or natural log q equals 0. If we speed up the forward rate of reaction relative to the reverse rate of reaction, we would just have to decrease the aluminum cation concentration and relatively increase the zinc cation concentration. And there's a squaring and a cubing effect, and that would create a lower fraction value for Q, or a more negative value for the natural log of Q, and we'd have that greater forward net rate of reaction, so that would increase the cell potential difference, increase the difference in attraction for electrons between the two half cells. On the other hand, as the reaction proceeds in the forward direction, the aluminum cation concentration builds up, increases, and the zinc cation concentration, due to its reduction, decreases. So we end up towards these lower and lower cell potential difference values until there is 0 cell potential difference at equilibrium, and that's when the forward net rate and the reverse net rate are equal to each other, and there'd be a 0 cell potential difference. So you may want to construct this galvanic cell that has a greater cell potential difference than 0.90 volts. Let's say you want it to be, I don't know, over 1 volt, or maybe 1.1 volts or something like that. You'd have to decrease the value of Q, or start with an initially low value of Q, by having a relatively faster forward rate of reaction. So you'd want to have a relatively higher concentration of the zinc salt, some soluble zinc salt, the source of the aqueous zinc cations, and a relatively low concentration of the aluminum cations. But, well, you can say, why don't I have a billionth molar aluminum? Well, good luck weighing that out. I don't know where you're going to find such a scale. So you have to use some kind of realistic, reasonable concentrations. So let's see what would happen if we had, let's say, 1,000-fold difference between the zinc cation concentration and the aluminum cation concentration. So let's try if we could find some soluble enough zinc salt to have a 2 molar initial zinc cation concentration and a 0.00150 molar aluminum cation concentration. If we could weigh out such a small quantity, or dilute the aluminum half cell enough to get that concentration. So we write out the equation, the Nernst equation, and then we plug in the numbers. Remember, Q is products over reactants, concentrations to their coefficients as exponents. We're producing aluminum cations, the aluminum is being oxidized, the zinc cations are being reduced. These are our current initial conditions, so we plug in the numbers and we get a cell potential difference greater than 0.90. So you see, even with a 1,000-fold concentration difference, the cell potential difference goes up by about 0.06 of a volt to 0.96 volts. So maybe not the giant answer you were looking for, but that natural log and the division by the small fraction, or the multiplication by the small fraction in front of it, really buffers or dampens the effect of a large potential difference change. But still, you know that could be quite a difference in a delta G value. On the other hand, if we had a relatively higher concentration of aluminum and a lower concentration of the zinc cation, higher concentration of the aluminum cation, that would have increased the value of Q and given you a lower cell potential difference, lower than 0.90, the standard cell potential difference. And that's mainly due to kinetics, and you can qualitatively solve these problems, or you could put in the numbers and quantitatively solve them. Just make sure you have the correct n and the correct q expression, and don't forget your exponents, and keep track of what's a product and what's a reactant.